Welcome, everyone. I'm excited to kick off today's presentation on states of matter. This is our first slide, titled States of Matter. We'll explore the different forms in which matter exists around us, from solids to liquids to gases, and even plasma. We'll look at their properties and how they change from one state to another. So, let's get started and discover the fascinating world of matter together. Now, moving on to slide 8, which focuses on the behavior of real gases and how they deviate from ideal gas behavior. In this section, we'll explore how real gases don't always follow the ideal gas law exactly, especially under certain conditions like high pressure or low temperature. We'll look at the reasons behind these deviations, primarily due to intermolecular forces and the finite size of gas molecules. Understanding these deviations is crucial because it helps us better predict the behavior of gases in real-world situations, beyond the simplified assumptions of ideal gases. This ties into the overall theme of the presentation by highlighting the importance of considering molecular interactions when studying gases and their properties. Let's take a closer look at the three states of matter. First, we have solids. Solids have a definite shape and a fixed volume because their particles are tightly packed together and don't move around much. This makes solids very rigid. Next, there's liquids. Liquids don't have a fixed shape. Instead, they take the shape of their container. Their particles are close but can move around each other, giving liquids their fluidity. Lastly, we have gases. Gases don't have a fixed shape or volume. Their particles are spread far apart and move freely, which allows gases to expand and fill any space available. Recognizing these states helps us understand how different materials behave in various environments, which is a key part of understanding matter itself and how it interacts in our world. Now let's look at the three states of matter: gases, liquids, and solids. On this table, we can compare their key characteristics. Starting with gases, they assume the shape and volume of their container, which means they can expand or contract as needed. Their particles can move freely past one another, allowing gases to flow easily. Gases are also highly compressible because of the large amount of free space between particles. Moving on to liquids, they take the shape of the part of the container they occupy. Their particles can slide past each other, which makes liquids flow smoothly. However, unlike gases, liquids are not easily compressible since there is little free space between the particles. Finally, solids have a fixed shape and volume. Their particles are locked into place, which makes them rigid. Because of this, solids do not flow easily and are not compressible at all. Understanding these differences helps us see how the microscopic behavior of particles influences the macroscopic properties we observe. This comparison is fundamental to grasping how matter behaves in different states. Now, let's take a closer look at intermolecular forces. These are the forces that act between molecules, and although they are generally weaker than the bonds within a molecule, they play a crucial role in determining the properties of substances. In this slide, I want to emphasize how these forces influence things like boiling points, melting points, and solubility. Intermolecular forces include several types, such as London dispersion forces, dipole-dipole interactions, and hydrogen bonds. Each of these has different strengths and impacts on molecular behavior. For example, London dispersion forces are present in all molecules, but they are especially significant in nonpolar substances. Understanding these forces helps us grasp why certain substances are gases at room temperature, while others are liquids or solids. Recognizing the strength and nature of these forces is key to predicting and explaining the physical properties of different materials. So, as we move forward, keep in mind that intermolecular forces are the microscopic reasons behind many macroscopic phenomena we observe in chemistry. Today, I want to talk about intramolecular forces, which are the attractive forces that occur between molecules. These forces are what hold atoms together within a single molecule, ensuring the molecule maintains its structure. It's important to understand that intramolecular forces are different from intermolecular forces, which we'll discuss next. Intramolecular forces are generally stronger because they involve the bonds holding atoms together, like covalent bonds. Recognizing these forces helps us understand the stability of molecules and how they behave in different conditions. Essentially, these forces are crucial for the integrity of molecules and, by extension, the properties of the substances we encounter daily. Let's talk about the difference between intermolecular and intramolecular forces. Generally, intermolecular forces are much weaker than intramolecular forces. For example, breaking all the OH bonds in a mole of water requires about 930 kilojoules, which is an intramolecular process. In contrast, vaporizing that same mole of water, which involves overcoming the forces between water molecules, only takes around 41 kilojoules. This difference is crucial because it explains why melting points and boiling points are much lower than the energy needed to break the bonds within molecules. The melting point and boiling point are good measures of the strength of intermolecular forces. The higher these points, the stronger the forces holding molecules together. So, when we look at these energy values, we see a clear distinction. Intramolecular forces are responsible for holding atoms together within a molecule, requiring much more energy to break, while intermolecular forces govern how molecules interact and are easier to overcome. This understanding helps us grasp why substances melt and boil at specific temperatures, related directly to the strength of these forces. Let's take a closer look at the different types of intermolecular forces. These forces are essential because they determine many of the physical properties of substances, like boiling points, melting points, and solubility. On this slide, we see that there are several main types to consider. First, there's London dispersion forces, which are the weakest and occur in all molecules, whether they are polar or nonpolar. They arise from temporary fluctuations in electron distribution that create instantaneous dipoles. Next, we have dipole-dipole interactions, which happen between molecules that have permanent dipoles. These forces are stronger than dispersion forces and influence how molecules align with each other. Then, there's hydrogen bonding, a special type of dipole-dipole interaction that occurs when hydrogen is bonded to highly electronegative atoms like oxygen, nitrogen, or fluorine. Hydrogen bonds are particularly strong and play a crucial role in the structure of water and biological molecules, like DNA. Understanding these forces helps us see why some substances are gases at room temperature, while others are solids or liquids. Overall, these intermolecular forces are key to understanding the behavior of different materials in our daily lives and in scientific applications. Let's take a closer look at the types of intermolecular forces. These forces are crucial because they determine many physical properties of substances, like boiling and melting points. First, we have London dispersion forces, which are the weakest but are present in all molecules, especially nonpolar ones. They arise from temporary fluctuations in electron distribution, creating momentary dipoles. Next, dipole-dipole interactions occur between polar molecules, where the positive end of one molecule is attracted to the negative end of another. These are stronger than dispersion forces and influence how molecules align. Then, we have hydrogen bonds, a special and particularly strong type of dipole-dipole interaction. They happen when hydrogen is bonded to highly electronegative atoms like oxygen, nitrogen, or fluorine, and this hydrogen then interacts with lone pairs on neighboring molecules. Understanding these different forces helps us grasp why some substances behave the way they do, and it ties directly into the overall theme of molecular interactions and their impact on material properties. Now, let's talk about the London dispersion force, which is actually the weakest of all intermolecular forces. It's a temporary attractive force that happens when the electrons in two neighboring atoms happen to be in certain positions. This creates a temporary dipole, or a short-lived separation of charge, in each atom. Sometimes this is called an induced dipole attraction, which highlights how one temporary dipole can induce a similar dipole in an adjacent atom. These forces are really important because they explain why nonpolar substances can condense into liquids and even solidify when the temperature drops enough. So, even though they're weak, dispersion forces play a crucial role in the behavior of many materials around us. Let's talk about dipole-dipole forces. These are attractive forces that occur between polar molecules. Specifically, the positive end of one molecule is attracted to the negative end of another. This kind of interaction is key to understanding how polar molecules behave in different environments. The strength of these forces typically ranges from about 5 to 20 kilojoules per mole, which means they are relatively weak compared to ionic or covalent bonds. However, they can still have a significant effect, especially when the molecules are very close together, touching or nearly touching. Remember, the proximity of molecules plays a crucial role in how these forces influence the overall properties of substances. So, while dipole-dipole forces are weaker, their impact is more noticeable when molecules are in close contact, shaping many physical properties of polar compounds. Let's talk about dipole-induced dipole attractions. These are relatively weak forces that happen when a polar molecule comes near a nonpolar species. The polar molecule causes a temporary dipole in the nonpolar molecule by disturbing its electron cloud. This creates an attraction, but it's not very strong, just enough to influence how molecules interact. Now, moving on to ion-induced dipole forces. These are similar in that they're weak attractions, but here, an ion approaches a nonpolar molecule. The ion's electric field induces a dipole in the nonpolar molecule by disturbing its electrons. This interaction is also weak, but important because it explains some of the behaviors we see in solutions and in molecular interactions. Both of these forces, dipole-induced dipole and ion-induced dipole, are part of the broader category called induced dipole forces. They play a key role in understanding intermolecular attractions, especially when dealing with nonpolar substances or ions. Recognizing these subtle forces helps us understand phenomena like solubility, boiling points, and molecular stability in various environments. So on this slide, we're looking at the idea that A and B are elements like oxygen, nitrogen, or fluorine. These are highly electronegative atoms, which is key to understanding hydrogen bonding. When we say a H, B, or a HA, we're talking about how hydrogen is bonded to these electronegative atoms, creating polar bonds. Now, the hydrogen bond itself is a special type of dipole-dipole interaction. It occurs specifically between a hydrogen atom that's part of a polar NH, OH, or FH bond, and another electronegative atom like oxygen, nitrogen, or fluorine. This interaction is quite unique because it's stronger than typical dipole-dipole forces, but not as strong as covalent bonds. It's crucial in many biological and chemical systems because it influences properties like boiling points, solubility, and the structure of molecules like DNA and water. So, understanding hydrogen bonds helps us see how molecules interact at a fundamental level, tying into the overall theme of molecular interactions that shape the behavior of matter. Let's take a closer look at gas laws, which are fundamental to understanding how gases behave. These laws describe the relationships between pressure, volume, temperature, and amount of gas. They help us predict how gases will respond under different conditions. For example, Boyle's law tells us that if we increase the pressure on a gas, its volume decreases, assuming temperature stays constant. Charles's law shows that if we increase the temperature, the volume expands, as long as pressure remains unchanged. These relationships are key to many real-world applications, from engines to weather forecasting. Overall, understanding these gas laws gives us a solid foundation for exploring more complex behaviors of gases in various scientific and practical contexts. So here we have Bulle's law, which is really fundamental when it comes to understanding gas behavior. The key idea is that at a constant temperature, the pressure of a fixed amount of gas is inversely proportional to its volume. In other words, if you increase the volume, the pressure decreases, and if you decrease the volume, the pressure goes up. This relationship is expressed mathematically as PV equals a constant, which means that the product of pressure and volume stays the same as long as temperature remains unchanged. It's a simple but powerful concept that helps us predict how gases will respond under different conditions. Understanding Buller's law is crucial because it lays the groundwork for more complex gas laws and helps us see how gases behave in real-world situations, like in syringes, engines, or even the atmosphere. Remember, the key takeaway is that pressure and volume have this inverse relationship when temperature is held steady. Chella's law states that, when pressure remains constant, the volume of a fixed amount of gas is directly proportional to its absolute temperature. In other words, if you increase the temperature, the volume will expand, and if you decrease the temperature, the volume will contract, as long as the pressure doesn't change. This relationship is really important because it helps us understand how gases behave under different temperature conditions. It's a key part of the overall theme of gas laws, showing that temperature and volume are closely linked when pressure is held steady. So, remember, in Chella's law, pressure stays constant, and the volume responds directly to changes in temperature. Today, let's talk about Gay-Lussac's law. This law states that, at constant volume, the pressure of a fixed amount of gas varies directly with its temperature. Essentially, if you keep the volume the same and increase the temperature, the pressure will increase proportionally. Conversely, if you decrease the temperature, the pressure drops. This relationship is important because it helps us understand how gases behave under different temperature conditions when their volume is held steady. It connects nicely to our overall theme of gas laws, showing how temperature and pressure are directly linked in predictable ways. So, remember, in Gay-Lussac's law, pressure and temperature go hand in hand when volume remains unchanged. So, this slide highlights a really interesting and fundamental concept in chemistry, which is that equal volumes of all gases, when measured under the same conditions of temperature and pressure, actually contain the same number of molecules. This might sound a bit counterintuitive at first, but it's a key idea behind Avogadro's law. What this means is that if you have, say, 1 liter of gas A and 1 liter of gas B, and both are at the same temperature and pressure, then they each contain the same number of molecules. It's a powerful concept because it allows us to relate volume directly to the number of particles, rather than just mass or other properties. This idea ties into the overall theme of understanding how gases behave and how we can measure and predict their properties. It's essentially the foundation for connecting the microscopic world of molecules to the macroscopic measurements we make in the lab. So, in summary, Avogadro's law tells us that under consistent conditions, volume directly reflects the number of molecules, providing a simple yet profound insight into the nature of gases. Now, let's explore the ideal gas equation. This equation is fundamental in understanding how gases behave under various conditions. It relates 4 key variables: pressure, volume, temperature, and the amount of gas, usually in moles. The equation is written as PV equals nRT. Here, P stands for pressure, V for volume, N for the number of moles, R is the ideal gas constant, and T is temperature in Kelvin. What's important to remember is that this equation helps us predict how a gas will respond when we change one of these variables, assuming the gas behaves ideally. It's a powerful tool because it simplifies the complex interactions between gas particles into a manageable relationship. This equation ties into the broader theme of understanding the physical properties and behavior of gases, which is essential in many scientific and engineering applications. The ideal gas equation is a fundamental relation that connects 4 key variables: pressure, volume, temperature, and amount of gas. It essentially describes the state of any gas, regardless of its specific type or conditions. Because of this, it's also called the equation of state. Understanding this equation helps us predict how gases behave under different conditions, which is crucial in many scientific and engineering applications. Throughout this presentation, we've seen how these variables are interconnected, and this equation ties all those concepts together in a neat, concise way. So, mastering the ideal gas equation gives us a powerful tool to analyze and understand gases in a wide range of scenarios. Now, let's take a closer look at Dalton's law of partial pressure. This law is fundamental in understanding how gases behave when they are mixed together. Essentially, it states that the total pressure exerted by a mixture of gases is equal to the sum of the pressures that each individual gas would exert if it were alone in the container. These individual pressures are called partial pressures. What's important here is that each gas in a mixture acts as if the others aren't even there, contributing to the total pressure independently. This helps us understand many real-world phenomena, like how inhaled oxygen and other gases interact in our lungs. By grasping Dalton's law, we connect the dots between the behavior of individual gases and the overall pressure in a system, which is key to many applications in chemistry and physiology. This law states that the total pressure exerted by a mixture of non-reactive gases is equal to the sum of the partial pressures of each individual gas. In other words, if you have a mixture, each gas contributes to the overall pressure as if it were alone in the container. This concept is really important because it helps us understand how gases behave together without reacting chemically. It ties into the overall theme of gas laws, showing how individual gas properties combine to influence the behavior of the mixture. So, when you're calculating the total pressure, just remember that it's the sum of all those partial pressures. Let's take a closer look at the kinetic molecular theory on gases. This theory helps us understand how gases behave based on the motion of their particles. Essentially, it states that gas particles are in constant, random motion. They move in straight lines until they collide with each other or with the walls of their container. These collisions are elastic, meaning no energy is lost during the process. One key point is that the particles are considered to have negligible volume compared to the space they occupy. This is important because it explains why gases are compressible. They can be squeezed into smaller volumes. Additionally, the theory assumes that there are no forces of attraction or repulsion between the particles, which helps us understand gases' ability to expand and fill their containers uniformly. Another crucial aspect is that the average kinetic energy of the particles is directly proportional to the temperature of the gas. So, as temperature increases, the particles move faster, which relates to the overall energy and pressure inside the gas. Connecting this to our overall theme, the kinetic molecular theory gives us a fundamental framework to interpret gas laws and behavior, linking microscopic motion to macroscopic properties like pressure, volume, and temperature. It's a powerful way to see how the tiny particles, movements influence the gases we observe and work with every day. So, the individual particles in a gas are neither attracted to nor repelled from each other, which is a key assumption of the kinetic molecular theory. The average kinetic energy of these particles depends on temperature, meaning the higher the temperature, the faster the particles move and the more energy they have. When particles collide with each other or with the walls of their container, they bounce off rather than stick together. These collisions are considered elastic, which means that if one particle gains some kinetic energy, another might lose some, so the total average energy stays constant over time. Another important point is that the particles are so tiny compared to the space they occupy that we can ignore their volume altogether. This helps simplify the model and makes it easier to understand the behavior of gases. Overall, a gas is made up of particles that are constantly in motion, and these assumptions form the foundation of how we understand gas behavior in the kinetic molecular theory. Now, let's talk about the behavior of real gases and how they deviate from the ideal gas law. While the ideal gas law is a great approximation under many conditions, real gases don't always follow it perfectly. This is because, in reality, gases have interactions between their molecules and occupy a finite volume. These factors become especially significant at high pressures and low temperatures. When molecules are close together, attractive or repulsive forces can alter their behavior, causing deviations from what we would expect if they were truly ideal. Understanding these deviations helps us better predict and work with gases in real-world applications, and it's a key part of the overall picture of gas behavior that we're exploring in this presentation. When Z is greater than 1, we call this a positive deviation. This indicates that the gas is less compressible than what we would expect from an ideal gas, meaning it doesn't follow the ideal behavior perfectly. In the case of real gases, the relationship PV is not equal to nRT, so Z is not equal to 1. Conversely, when Z is less than 1, we have a negative deviation, which shows the gas is more compressible than ideal gases at the same conditions. This leads us to understand that for real gases, Z can be either less than 1 or greater than 1, depending on the conditions. Now, for an ideal gas, the equation PV equals nRT always holds true, so Z equals 1. A gas that obeys these gas laws, and the equation PV equals nRT at all temperatures and pressures, is called an ideal gas. The molecules of such gases are considered to be point particles with no volume and no attractive forces between them. However, in reality, no gas strictly follows this at all times, mainly at high pressures or low temperatures, where deviations become more significant. To account for these deviations, we introduce the compressibility factor, Z, which helps us understand how real gases differ from ideal behavior. By calculating Z as PV divided by nRT, we get a measure of this deviation. This factor is key to understanding the behavior of real gases in various conditions. Let's talk about why gases sometimes behave differently than what the ideal gas law predicts. One key reason is that the forces of attraction between gas molecules are actually negligible. In other words, these molecules don't really stick to each other. They mostly ignore each other, which simplifies their behavior in many cases. Another important point is that the volume occupied by the gas molecules themselves is extremely small compared to the total volume of the gas. This means we can usually ignore the actual size of the molecules when considering how gases behave, especially under ideal conditions. However, these assumptions, like molecules not attracting each other and being point particles, are not always perfect. Deviations from ideal behavior happen when these assumptions break down, which can occur under high pressure or low temperature. These deviations are directly linked to the core ideas of the kinetic theory of gases, which simplifies gas behavior based on those assumptions. So, understanding these causes of deviation helps us better predict and explain real gas behavior, especially in practical situations where gases don't exactly follow the ideal model. Let's take a closer look at the van der Waals equation. This equation is really important because it helps us understand how real gases behave differently from ideal gases. Unlike the simple ideal gas law, PV equals nRT, the van der Waals equation introduces two correction factors. These factors account for the actual size of molecules and the intermolecular forces between them. The first correction, involving the volume term, adjusts for the fact that molecules occupy space and aren't just point particles. The second correction, related to pressure, accounts for the attractive forces pulling molecules together, which reduces the pressure exerted on the container walls. By incorporating these corrections, the van der Waals equation provides a more accurate description of gases near condensation points and at high pressures. It's a key step in bridging the gap between ideal models and real-world behavior, helping us better predict and understand the properties of gases under various conditions. Atoms and molecules are never truly ideal because they all interact with other gas particles. These interactions are usually weak attractions between separate gas particles, and we call them intermolecular attractions or van der Waals forces. These forces are named after the chemist who proposed a correction to the ideal gas law to better account for the behavior of real gases. Van der Waals suggested that the ideal gas equation could be modified to reflect real gas behavior. He proposed subtracting the effective volume occupied by gas particles from the total volume of the container. Additionally, he recommended correcting for the attractive forces between particles, which tend to reduce the pressure exerted by the gas. This leads us to the van der Waals equation, which provides a more accurate description of real gases by incorporating these corrections. Understanding these concepts helps us see why real gases deviate from ideal behavior, especially at high pressures and low temperatures, and ties into our overall theme of understanding gas laws more comprehensively. Now, let's take a closer look at the properties of liquids. Liquids are fascinating because, Unlike gases, they have a definite volume but no fixed shape. This means they can flow and take the shape of their container. One key property is surface tension, which is the result of cohesive forces between liquid molecules at the surface. This is what causes drops of water to form into spheres and allows small insects to walk on water. Another important property is viscosity, which is basically a liquid's resistance to flow. Think of honey versus water. Honey has a high viscosity and flows slowly, while water flows quickly with low viscosity. This property affects how liquids behave in various situations. Additionally, liquids exhibit compressibility, but to a much lesser extent than gases. Their molecules are already close together, so compressing a liquid requires a lot more effort. Understanding these properties helps us grasp how liquids behave in real-world applications, from designing hydraulic systems to understanding natural phenomena. So, when we talk about the properties of liquids, we're really exploring what makes these substances unique and how they interact with their environment. The pressure exerted by the vapors in equilibrium with liquids of the same substance is called the vapor pressure of the liquid. This concept is important because it tells us how easily a liquid vaporizes at a given temperature. When a liquid is in a closed container, some of its molecules escape into the air as vapor, creating a pressure. As more molecules escape, the vapor pressure increases until it reaches a balance with the molecules returning to the liquid. This equilibrium state is what we refer to as vapor pressure. Understanding vapor pressure helps us grasp how liquids evaporate and how they behave under different conditions, which ties into the overall theme of phase changes and intermolecular forces. It's a key factor in processes like boiling, evaporation, and even in designing various industrial applications. Surface tension is the force acting per unit length perpendicular to the line drawn on the surface of the liquid. What this means is that, at the microscopic level, molecules at the surface experience an imbalance of forces because they are not surrounded by similar molecules on all sides. This imbalance creates a force that acts to minimize the surface area of the liquid. Essentially, the liquid behaves as if its surface is covered with a stretched elastic sheet. This is why small droplets tend to be spherical. They naturally adopt shapes that minimize surface area due to this tension. Understanding surface tension is crucial because it influences phenomena like capillary action, droplet formation, and even the way insects can walk on water. So, in the broader context of fluid behavior, surface tension helps us explain many everyday observations and is fundamental to the study of liquids. And with that, we come to the end of our presentation. Thank you for your attention. Remember, viscosity is essentially a measure of how resistant a liquid is to flowing. It's closely related to the intermolecular forces. Stronger forces mean the liquid resists flow more and thus has a higher viscosity. Understanding viscosity helps us grasp how different liquids behave in various situations, whether it's in industrial processes or everyday life. So keep in mind that the key takeaway is, the stronger the intermolecular attractions, the more viscous the liquid. Thanks again for joining me through this chapter. Hope you found it insightful.